Today, we're going to be talking about the oxidative cleavage of alkynes. Now, we did an oxidative cleavage reaction when we studied the alkenes, and so I would like to do a brief review of that before we get into the alkynes. If you look back at your notes, you'll see that you could do an oxidative cleavage of an alkene, and you could do it either through ozonolysis or by permanganate oxidation in hot concentrated KMnO4. The products that were produced if you did an ozonolysis of an alkene were aldehydes and ketones. If you did the oxidative cleavage using hot and concentrated potassium permanganate, then the products were carboxylic acids and ketones, or in the case of the monosubstituted alkene, you formed carbonic acid, which then produced carbon dioxide. All right, let's now look at the oxidative cleavage for the alkyne. For the oxidative cleavage of the alkyne, you'll want to look at what type of alkyne you have. If you're looking at a terminal alkyne, then your triple bond is at the end of your carbon chain as opposed to an internal alkyne where the triple bond is somewhere other than the end of your carbon chain. When doing an oxidative cleavage of a terminal alkyne, just like in an alkene, you'll be cutting between the carbons of your triple bond the same way you cut between the carbons of your double bond. This will break or cleave the molecule or the carbon chain into two pieces. Looking at our triple bond on the terminal alkyne, the carbon that is on the left-hand side is attached to an ethyl group, and so when you cleave it, there are 3 carbons in that piece. Looking at the carbon on the right-hand side, it is attached to a hydrogen. So when it is cleaved, there's only 1 carbon in that piece. Now, cleaving the triple bond will result in the production of a carboxylic acid, and in the case of a terminal alkyne, it produces carbonic acid. And if you remember from the oxidative cleavage of our alkenes, when carbonic acid is being produced, it is not stable, so it would rapidly break up into carbon dioxide and water. Excuse me. So your textbook actually doesn't even draw it out as carbonic acid. It says in the oxidative cleavage of the terminal alkyne, you will create a carboxylic acid and carbon dioxide. Looking at the internal alkyne, you're still going to be cleaving the carbon chain between the 2 carbons of your alkyne. The carbon on the left is connected to an ethyl group, so it produces a 3-carbon carboxylic acid. The carbon on the right is connected to one other carbon. So it also produces a carboxylic acid, but now it has just a 2-carbon carboxylic acid. So, in summary, when doing an oxidative cleavage of a terminal alkyne, you will produce a carboxylic acid that is 1 carbon shorter than your original terminal alkyne, and it will produce carbon dioxide. When doing an oxidative cleavage of an internal alkyne, it will produce 2 carboxylic acids, and the size of the carboxylic acids will depend on where the triple bond is in your chain. Okay, now this is where it is different from an oxidative cleavage of an alkene. When we looked at the oxidative cleavage of an alkene, and I'll go back to that page of your notes, we saw that the ozonolysis of an alkene would produce aldehydes and ketones, but the permanganate oxidation of the alkene produced carboxylic acid and ketones. Comparing that to the oxidative cleavage of the alkynes, what we'll find is that ozonolysis of the alkyne and permanganate oxidation of the alkyne using hot and concentrated potassium permanganate produce identical products. So ozonolysis produces carboxylic acids and carbon dioxide for a terminal alkyne, and permanganate oxidation does the exact same thing. Ozonolysis of an internal alkyne produces 2 carboxylic acids, and that is identical for the permanganate oxidation in hot concentrated KMNO4. And I'm just going to remind you, here is our carbonic acid that is going to break up into carbon dioxide and water. And I will note that for you because your textbook says that the oxidation of a terminal alkyne, the permanganate oxidation or the ozonolysis of a terminal alkyne produces carbon dioxide. Okay, that means that if you see the products of the oxidative cleavage of an alkyne, you wouldn't be able to tell whether it was an ozonolysis or a permanganate oxidation because they do produce the same products. However, you would be able to tell whether it was a terminal alkyne or an internal alkyne because only the terminal alkyne will produce CO2. So if I were to do an example, there is my alkyne. You can see that it is an internal alkyne, so you should expect the oxidation, whether you use ozonolysis or permanganate oxidation to produce 2 carboxylic acids. I look at the carbons. The one on the left is attached to 5 other carbons in the chain. The one on the right has 3 more carbons on the chain. So when doing my oxidative cleavage, and I'm going to do ozonolysis, but you could do permanganate oxidation with hot and concentrated KMNO4. We'll cleave it, and we'll have 1, 2, 3, 4, 5, 6 carbons from the left. There's my carboxylic acid. And we will have 1, 2, 3, 4 carbons on the right. And those would be the products of the oxidative cleavage of an alkyne. Okay, now I want to do a little bit of a compare and contrast again with the oxidative cleavage of an alkene. We can see that oxidative cleavage of the alkyne produces carboxylic acids and carbon dioxide. Oxidative cleavage of the alkene might produce aldehydes and ketones, or carboxylic acids and ketones, depending on whether ozonolysis or permanganate oxidation is used. So, if you look at the products of an oxidative cleavage, sometimes you will be able to tell the starting material's functional group depending on what you see as the products being produced. I'll show you what I mean. Let's take the case of looking at the products of an oxidative cleavage, and if you see that the products are aldehydes. When you do an ozonolysis. Well, ozonolysis creates aldehydes from alkenes, but it produces carboxylic acids from alkynes. Then that would mean that you started with an alkene. That's the same thing if you saw any aldehydes, even if you had an aldehyde and a ketone when you did an ozonolysis, it had to come from an alkene. If you saw that your products were ketones when ozonolysis was used, again, that also means that it came from an alkene. Okay, so think about how you would be able to tell if it came from an alkyne. Well, the products that you see would be carboxylic acids, or carboxylic acids and carbon dioxide. When you use ozonolysis. And if you see that the products of an ozonolysis were carboxylic acids, then that must mean that your starting material was an alkyne. Okay, but what about if you did a permanganate oxidation instead of an ozonolysis? Well, sometimes you can still tell what your starting material was. It just depends on the situation. So, for example, if you saw that the products were equal to carboxylic acids, or carbon dioxide, and ketones, the carboxylic acid and the ketone, well, the ketone could only have come from an alkene, not from an alkyne, because the products of an oxidative cleavage of an alkyne is only carboxylic acids. So seeing a carboxylic acid and a ketone, wherever you see the ketone, it must have come from an alkene. So the one that stands out is, what if your products are both carboxylic acids? From a permanganate oxidation. Oh, and this one was from permanganate. Oxidation. Okay, if your products are both carboxylic acids when doing oxidative cleavage using permanganate oxidation. Now, that's the only one that you don't know for sure. It could be you started with an alkene, because alkenes can produce carboxylic acids. It could be that you had an alkyne, because those also produce carboxylic acids. Now, not every single type of alkene, but let's say an alkene like this, permanganate oxidation would produce the carboxylic acids from that alkene. And oxidative cleavage by permanganate, hot concentrated permanganate, would also produce carboxylic acids from that alkyne. So that's the one where you can't tell just based on the products that are being produced in the reaction. The other cases, with the ozonolysis, you could always tell whether you started with an alkene or an alkyne. And for the permanganate oxidation with the concentrated potassium permanganate, you can tell if your product is a ketone because only the alkenes can produce ketones. But if you only see carboxylic acids in the oxidative cleavage using hot concentrated permanganate, then your starting material could be an alkene or it could be an alkyne, and you're going to have to use other types of tests to figure out whether it's an alkene or an alkyne. You can't tell solely on the basis of the oxidative cleavage products.